Hello everyone, welcome to my first tutorial video on Chem 2B, and we're starting with chapter 9. So this video is going to be just a quick summary and explaining most, if not all, the concepts in chapter 9 that you're going to learn in Chem 2B. And get straight to the point, we start with systems. When it comes to systems, there are three different types of systems that you're going to see in this class. Actually, I think that's all the kind of systems they are in general. And the first one is an open system. And the open system is, like the name says, it's open. It's both open to energy and matter transferring in and out. A closed system is open to just energy transferring in and out, but matter can't. And then an isolated system is none, neither energy nor matter transfer in or out. And when it comes to this class, especially in this chapter, energy and heat, you can basically think of them as interchangeable, where they're both represented by the kill sign and they both mean energy and heat, because heat is basically just energy transferred between objects. And when it comes to heat, there are different signs that you can associate with heat. So when the sign is negative, it means that the heat is leaving the system. And when a system has heat leaving the system, we call that exothermic. And in an exothermic system, reactants tend to have more heat than the products, so it's more reactants favored. And then when the sign is positive, like when the kill is positive, that means that he is entering the system, and that's usually known as endothermic, which is different from exothermic, and it's more means that there's more heat in the product side. So the reaction is basically product favored instead of reactants. For this class, one of the most important equations that you'd have to know regarding heat, or one of the most used equations, is that Q equals to mc delta T. And basically this equation, it's easy to remember because it sounds like MCAT, or it looks like MCAT. And what each of the variables mean is that the M, easy to remember, it's the mass, and then the C is the I think it's heat capacity, because they're different things. There's heat capacity and specific heat. I think this is the heat capacity. And then the last term, which are together, the change in T, is basically, like it says, the change in temperature. So if the final temperature minus the initial temperature. So let's say something goes from 50 degrees Celsius to 100 degrees Celsius. The change in T is basically 100 minus 50, which gives you 50. So that's going to be the change in T. And when it comes to this equation as well, the kind of important thing to know, well, not kind of, it's really important to know, are the units. So a lot of the times, even if you do get lost in these equations, the units always bail you out, because when you write them out and you cancel them, there's certain units they're supposed to end with, and how you know you did it right. So the mass is always going to be in grams for this class, and then so whatever mass they give, let's say they give you kilograms, you're supposed to transfer it in grams, and then do the equation like that. The temperature, normally for the rest of the class, it's usually in Kelvin, but for heat capacities and stuff like this, it's written in Celsius. And then the kill obviously is going to be in joules or kilojoules, because that's energy and heat. And then the heat capacity is written as J, which is the joules, divided by the grams per Celsius. So the temperature, and this works because if you do grams times joules over grams of C times C over 1, this cancels, the G cancels, the C cancels, and you're left with joules, which is what Q is supposed to be in joules. Okay, so I basically told you what the different components of the heat equation is, but what do each of them mean? So the grams, well, that one should be obvious. It's just the weight or the mass of the substance that is basically what you're trying to calculate. You could see, I'm going to do a practice problem and show you what the the grams should be easier to identify. And then secondly, the heat capacity. So I gave you the unit for it. It's this. But what does this mean, if you would ask? So this basically means the amount of, so the heat capacity is the amount of energy, which is joules, it'll take to heat up 1 gram of a particular substance up 1 Celsius degrees. And different substances have different heat capacities. For example, off the top of my head, because I've done it so many times, I remember water's heat capacity is 4.18. And something else like aluminum is lower on the spectrum. I think it's 0.90. And what this basically means is that water, so one of the properties of water is that it takes a lot of energy to heat up water. So what this means is that it takes 4.18 joules to heat up 1 gram of water up 1 Celsius, while it only takes 0.9 joules to heat up 1 gram of aluminum up 1 Celsius, just like water. So from the heat capacity, you can also kind of use deductive reasoning. Like, let's say they ask you a question on a test, like if you put aluminum and if you put water together, which is going to be the fastest to heat up? It's going to be aluminum, because it has the lower heat capacity. That means it takes less energy to heat it up the same amount. That if you put 5 joules into both water and if you put 5 joules into aluminum, see how aluminum is going to heat up a lot more, because like basically it's going to heat up 5, you're going to be able to heat up 1 gram of aluminum up 5 degrees Celsius, because it's going to go up 5 versus water is only going to go up approximately 1 Celsius. And that's what heat capacity means. And the last unit is just temperature, which you should also know what temperature means. That's just, it's measured in Celsius, and it's going to be also obvious to see in the question that I'm going to show an example now. This is an example of a simple problem that just encompasses the concepts that I just talked about. So this problem is asking, you can read the problem, 250 grams of sample water heated from this to that, calculate the amount of heat. So this is a simple problem, and how to do this is, how to solve problems like this is you look at what it's asking for. It's asking for the amount of heat in joules, and you know from that equation that heat is kil. So you're looking for kil from this equation. All right, and it also says joules. So there are 2 different units that you're gonna use in this class for heat. Is usually kilojoules or joules, and this time it's asking for joules. And the conversion between these units is joules is divided by 1,000 to get kilojoules, and then kilojoules is multiplied by 1,000 to get joules. All right. They give us also another thing is that you never have to worry about memorizing the heat capacities for things, because usually they either give it to you in the question or on the test. There's like there's a equation packet that you get, and it usually has the heat capacity. So for this question, you basically know the formula here, and we're gonna substitute in the right things for the formula. So we're lucky enough that they gave us the grams, the mass in grams and not kilograms, and we have to start converting all the way to grams. So you just put 250 grams here multiplied by the heat capacity, which is here to 4.18 joules slash this. And then finally, the temperature. Since it's a change in temperature and not just one, what you do is you try to find, so you're changing it from this to this. So that means this is going to be the final temperature, and this is the initial temperature that you're starting with. And the change in temperature is multiplied by the final temperature minus the initial temperature. So here we put 75 minus 22, and the rest is all plug into a calculator, and you get the final answer. When you plug into your calculator, this all gives you 55,385 joules. The reason why the units end up being joules is that when you look at the equation again, the grams cancel out, and then I forgot to add this, but this has a Celsius in it, and The Celsius also cancels out and you're left with joules right there. And let's say the question asks you to put it in kilojoules instead. What you do is that you basically multiply it. So this is in joules, and then you multiply it by, multiply or divide by 1/1000, and it gives you the answer in kilojoules. So you just move it to 1, 2, 3, and it becomes 55.385 kilojoules. Okay, now that I've basically explained what heat is and how to solve for it in a question like that, I move on to the next topic of the class, which is going to be the first law of thermodynamics. And basically what this law says, well, it's kind of widespread, so a lot of people know what it already means, and it's still the same here in this class, is that energy can't be created nor destroyed. How this concept is expressed through this class is through the concept of something called a calorimeter. So I mentioned earlier how there are different systems, and they're isolated, closed, and open system. In an isolated system, this law must hold through, where energy can't be created nor destroyed. So for example, like you've probably heard of this in this class, a calorimeter, which is a cup, closed cup, and only one thing goes in it, covered, blah blah blah. Energy can't leave nor enter this cup. So every reaction that's going on in this cup, you can't destroy energy, so it can't. So the sum of all the reactions can't be negative because you can't destroy energy, and it can't be positive because you can't create energy. So this is all, they're all gonna sum to 0, and the sum of the reactions is equal to the sum of the energy in the cup is equal to the heat or the energy of all the reactions plus the energy of the calorimeter. And what this does, since this is always 0 in a calorimeter, equals 0 equals to the Q of the reaction plus the Q of the calorimeter. And then you can leave it this way and remember it like that, about how in an isolated system, the sum of all the Q's is always going to be 0. So they can be more, like they can be random things, like add more things to the, more equations, more processes, like more stuff can be added to the calorimeter, but it's all going to sum to 0. And this might be hard to understand right now, but after I just show a practice problem, you'd get it more. But before I should go to a practice problem, I'm going to describe this Q instead. So the Q reaction is basically what we did earlier, where you solve for the Q given the mass, the specific heat, and the temperature change. But for the Q of the calorimeter, since the calorimeter is the system itself, it doesn't have a mass, the Q of the calorimeter is just going to be the specific heat of the calorimeter times the change in temperature of the calorimeter. There's no mass that goes on here. This is an example of one of those problems where, although it's not stated specifically, you are trying to solve for the total sum of energy in this equation, in this system. And remember, the sum of all the Q's always has to be 0. So now we identify the different Q's, so like the different processes going on in this one particular system. The first one is water right here. It says 40 grams of water. You're going to be solving for the Q of water. And then another one is for the Q of copper. And then it says it right here, what mass is required to reach 40 degrees Celsius. So for this, you're not essentially solving. So the question, you're looking for the mass of the copper. And then remember the equation, Q equals to MC delta T. You're given the mass of water. You're given the specific heats right here, specific heat of water, and you're both given the temperatures. This is going to be the initial temperature because it says it starts at 50 and then they're trying to reach 40. So this is going to be the final or the target temperature. And then you have both the starting and the initial and the final for water, and also you also have the initial and the final for copper as well. Right here, this is the initial for copper. So you identify the stuff that you're given, and you try to find what you're not given. So these are the two equations. This is for kil of water, and then for copper you have the same thing, except we're looking for the mass of copper, but then we have everything else. And this is going to be kil copper, and we know that this equation, so the sum of all the kils is kil water plus kil copper. And then since this is 0, we know that to find they both, so when you move one of the equations to the other side, or actually we won't move it for now, we'll just leave it like this, and then you can move this equation and have it kil water equals to negative kil copper, but it doesn't matter. You can do it like this, and I'll show you how to do it like this in the problem. So after we have the components and we know the equation we're supposed to use, we start filling in the blanks, and it's the kil of water plus the kil of copper, and we know the equations for both of them right here, and we start putting it in. So the kil of water, it's going to be 0 is equal to the kil of water is the mass, which is 40 kilograms. Remember, we use grams, so we have to convert 40 kilograms to grams. So what we do is just we multiply by 1,000, and it becomes 40,000 grams of water times the specific heat of water is given right here, 4.18 joules times GC times the change in temperature of water. It starts at 50 and the target is for 40. Both of them have targets of 40. So that means the final is going to be 40 minus 50 degrees Celsius. And then this is the kil of water. And remember, you add it with the kil of copper. And for this copper, we don't know the M, so we're going to leave it as M since they never give us the mass. That's what we're looking for. But we do know the heat capacity of copper, which is 0.385 joules per gram Celsius. And we also know the initial and the final temperature is going to be the same, 40. Actually, no, not 40. Copper starts at 15. Actually, it is going to be 40, but copper starts at negative 15. So instead of 40 minus 50 like we did here, it's going to be 40 minus negative 15, which turns to a plus instead of a minus. Now we simplify this. I'll start plugging into the calculator to get all this and then all that. After you multiply all this, the kil of water comes out to be negative 1672 and then 000, and this is joules, plus it's still M, we don't know M, multiplied by these two multiplied together gives you 21.175. And the units for this is joules per grams, and the mass is going to be in grams, and we don't know what that is yet. So this is still equal to 0, and it basically becomes algebraic. We're doing algebra now, we're trying to solve for M. So we'll move this to the other side, and it comes 1672000 equals to M times this. And now you divide both sides by this to leave M isolated. And then when you divide both sides by 21.175 joules per grams, the joules end up canceling. Cut this part out. The joules end up canceling out, and you're left with grams, and you're left with about M is equal to 78,961 grams approximately, and that's the mass of copper needed for this equation to be proven right. And you can also change this to kilograms back to kilograms because they gave you the mass of water in kilograms. And what you do is divide it by 1,000. So you move the decimal points 3 times to the left, and then it becomes 78.961 kilograms. And that's the mass of copper you need. And not only in this chapter are you going to learn about things like heat, which is Q, you're also going to learn about another energy. What I say, way of expressing energy is also work. And work is, if you've ever taken a physics class, you know work is the amount of energy you put into something. Just basically amount of energy, amount of force you put for distance. But then in this class, we're not going to be doing the physics kind. We're going to be using work for for chemistry. And the equation that would be given to you in this class is work is equals to negative P delta V, which is, it means the pressure times the change in volume. But then from the ideal gas law that you did in Chem 2A, you can also derive that work is also equal to negative delta N RT. There's a way to derive it from that, but then you don't really have to know if it confuses you along the way. Just know that there are 2 different ways of writing work in this class. And it depends on the kind of problem. You're going to have to know how to use both of them. But it's easy to recognize which work equation you're going to use. Like if the multiple choice gives you the change of volume, which this equation has, obviously you know you're going to use this one. But if it gives you the change of moles instead, and they ask you to solve for the work, you're going to use this one. And another thing is, there's something called the internal energy of something. Like every system has an internal energy, and that internal energy is comprised of the amount of heat plus the amount of work that that system does. And it makes sense because, let's say, think of a system that does a kind of a system, yeah. It has a certain amount of energy in it, and then if that system has to do some work, it's going to give off that energy. And remember, when it's giving off energy, it's endothermic. It's also the same in work, it's a negative. But then when it's having work done on it, it's gaining energy. So when a system has energy and it requires work to be done in something else, it's going to cost energy. But then when something else is doing work in a system that already has energy, it's going to gain more energy. And that's why this equation stands. The internal energy is the heat plus the work. And yet another thing, all these things are called state functions. So they're the capital letters. Like imagine this, you have to get from your house to your school. You can go a straight path that's only 5 feet long, and you only take 5 feet from your house to your school. Or you can go to your friend's house, go get ice cream, go do something else, and then finally go to school. In this path, let's say it takes 15 feet instead. You're still going from point A to point B, but you're taking a much farther distance to get to point A to point B. While if you take the standard, if you take away all the extra things that you did to get to school, it should only take you, it's 5 feet. It's basically these are called state functions in chem. And something like the internal energy. Let's say you start with an internal energy of 1 joule, and then for the kill, you have about 1 joule as well, 1 joule of heat in you. But then you do work that, let's say you do work on a system that cost you 5 joules, but then another system does work on you that also cost you 5 joules. So in total, you spent 5 and you got 5 back, but then at the end of the day, it still got you back to this 1 joule right here. The 5 minus 5 gives you 0, so it cancels out. That's why this is a path-dependent function, and this is also a path-dependent function, because you can also have 10 joules of heat and then given out, and then also receive 10 more joules of heat. So the path, like, do you get what I'm saying? The path doesn't matter. The path you take, you could do a CERN, you can do all this work, and then you can go back and have all this work given to you, but you'd still end up in the same place, and that's what U tells you. U tells you the internal energy went from either 0 to 1. It doesn't tell you all the work, all the extra work it did, and all the work that was done for it to average at to come back to 1. And that's why this is a state function, and these aren't state functions. And another state function that you learn in this class is enthalpy. To oversimplify enthalpy, enthalpy is basically the heat kill, but then at constant pressure, which most of the time when you use enthalpy in chem problems in this class, they're going to tell you it's at constant pressure. So you don't have to remember much, but basically enthalpy is the same thing as Q. And the equation for enthalpy is directly derived from the equation from Q, because if you remember, U equals to Q plus W, and W is also equal to negative P delta V. Alright, so if Q is the same thing as enthalpy, which is this, it becomes the change in U equals to the enthalpy plus, and then work is this P V, and then it becomes P, instead of a plus, it becomes a minus P delta V. And then when you solve for enthalpy alone, you move this to the other side, you add P delta V to both sides, and then it becomes the enthalpy equals to the internal energy plus P delta V. And that's how you get the equation for the enthalpy. One thing to know about enthalpy is that usually when they give you the enthalpy of something, let's say it's like 2, it's 2. The units are usually in kJ over mole. And when they give you something like this, you're supposed to recognize the mole. This mole right here, this is basically energy over per mole of something. So then to find the pure energy, you multiply it by, let's say there are 2 moles, 2 other moles of a particular substance. You multiply 2 moles of that substance times 2 kJ over moles. The moles cancel out, and you're basically left with 4 kJ, and that's the actual amount of heat per 1 mole of that substance. Okay, let's do a problem that encompasses both of the things that I just explained in the video about heat capacity and now enthalpy. This is basically enthalpy, the kilojoules per mole unit that they give. And this problem, so first of all, the problem gives you the heat. It doesn't give you, it's asking, it's determining cut. Okay, so first we can start with the first part of this question A, which is just asking for the balanced reaction. So it's just asking for the equation for burning propane, this. And one thing to know when a question asks something like this, it's that the thing that is being burned, propane, is always written in, it's always 1 mole of propane. So it's just this, C₃H₈. This is always going to be how you start every question that asks you for combustion, the reaction for combustion. And if you know maybe from previous science classes, fire is burned by oxygen. So like without oxygen, you can't burn. Fire can't happen because that's how the reaction works. So every combustion reaction should have the gas, which is propane for this one, plus oxygen. And don't worry about balancing it yet. At the end, after you write it down, you balance it. And this becomes, and remember, when fire burns, it gives off H2O and carbon dioxide here. And now you've written all the components for a combustion reaction, you can start balancing it. And remember, you only have 1 mole of this, so this is how the easiest way to balance it. You know that this isn't going to change, so other things have to adjust to meet this. Like the propane has 8 oxygens, and this only has 2 on this side of the equation. And if you remember how to balance equations, you know that both sides must have the same amount of things and same amount of elements. Since this side has to have 8, that means there has to be 4 H2Os, which makes 8 oxygens. And then this side only has it has 3 carbons. So that means the CO2 also has to be 3. And now you balance the C and the H on this side, you balance the O on this side, which here you can see there's 4 O's, H2O gives us 4 O's, and then carbon dioxide gives us 3 times 2, 6 O's. And then you add both of them, and then here is 10. So this gives you 10 O's to balance the 4 plus 6 O's on this side. And then the C's are balanced and the H's are balanced as well. Oh, but one mistake that I made in this is that the O2, usually in an equation, O's never written alone. Like, I'm not sure about this, but in general in chemistry, from what I've seen so far, is that the O is always O2. Like, these are, an O alone is an unstable element, so it's always partnered. Like other things like H's, they're not usually written alone. O's aren't usually written alone. I forgot but other elements aren't usually written alone, so this becomes 5 instead of 10. Okay, now that you've answered the first part of the question, you can move on to the second part, and it's talking about heat capacity. And the BOM is basically a kind of calorimeter. It's called a BOM calorimeter, and just like a calorimeter, the heat capacity is, this is the equation for it, and then the C is the heat capacity. So how you find that is it's equal to when you solve this, you divide this to the other side, so it's Q over the change in temperature. And then when we look back up here, so you know Q's energy, and they give us the energy of the combustion. So we are given the energy of the conversion. But when you look over here, you see that it's per mole. This is why units are a big part of this class. So if you try to do this question without looking in the units and you just use that number, you're going to get it wrong, because the units have to be, the energy units has to be in either joules or kilojoules. It can't be kilojoules per mole. So how we find the energy from this energy they give us, so they give us negative 2,220. We are given negative 2,220. Oh, that's wrong. Negative 2,220 kilojoules per mole. And we're trying to put it in kilojoules. So what we have to do is to multiply it by the mole. And up here, another trick for this class is that when you're usually given the formula for the substance propane that we're using, it's usually, sometimes they determine you to find the molar mass. And how to do that is just to multiply. So multiply the molar mass of C times 3 and the molar mass of H times 8, and it gives you the entire molar mass. And instead of wasting time doing that in this video, I'm just going to give you the actual molar mass itself. The molar mass for propane turns out to be approximately 44.01 grams per mole. And now they give us a certain amount of grams. So they gave us 5.25 grams. This is basically stoichiometry that you can learn in Chem 2A, how to convert from moles to grams to all that molar mass. So we do this, we write out 5.25 grams, 5.25 grams. And we're trying to find the moles. So we put the moles on top times 1 mole of this over 44.01 grams. And the grams cancel out, leaving us with the moles. And then we divide these two numbers. We get that there's approximately 0.119 moles of propane in this reaction. And now we can find the total energy, which is negative 220. I keep making that mistake. 2220 kJ over moles. I'll write it this way: kJ over moles times 0.119 moles The moles cancel out, and you're left with negative 260, approximately 65 kJ, which is the heat. This is equal to the kill. Now, we're not looking for the kill. This isn't the final answer. We're trying to find the heat capacity, which is given by this equation. Kill C equals to this over this. So now for this question, we already know what the kill is. We solved it right here. The other part is the change in T that we're looking for, the change in temperature. If we scroll back up to the question, you can see that the change in temperature is given right here, 14.2. We don't have to do the find minus the initial because they already gave it to us right here. And we can just plug it into the equation. So the equation becomes the heat capacity is equal to negative 265 kJ over 14.2 degrees Celsius. And normally the heat capacity in this class, the ones you're going to be using have units of joules, but since this is such a large energy, I'm just going to leave it in kilojoules instead of multiplying it by 1,000. And finally, the final answer to this is 18.66 kilojoules per degrees Celsius. And another thing is that, so when you divide these two things, you get a negative answer, but the specific, the heat capacity can't be negative. So it's just the absolute value of whatever you got from this, all this. Now that we've figured out the heat capacity of the calorimeter bomb, we can move on to the next question. And I think this question is dependent on the answer we get here, but we'll read it first. So there is, look at the numbers, 10.8 grams of a new substance. Instead of the last one, we used propane, but this time we're going to be using ethanol. And this problem also gives us the temperature right here. And then at the end, it says, what is the energy of combustion? So we're basically looking for the kJ/mole. So we're looking for, our answers have to end with a Q. And also, you see this mole part? See how nowhere in the problem did they give us the moles? That means we're going to have to convert this grams to moles. And also right here, they gave us the equation as well. That gives us a way to find the molar mass and then convert the grams to moles. But before we go about finding the moles, we have to find the energy of the calorimeter. And remember, since although they give us the grams here, we're trying to find the energy of combustion. We're not trying to find how much this changed. We're not trying to find the energy to change ethanol. So we're not going to necessarily use the grams for the first part of the equation. And the energy for a calorimeter is the heat capacity. The same calorimeter, by the way, from the earlier problem. So we already solved for this, the heat capacity times the change in temperature, which they gave us to us right here. And to do that, it's equal to the 18.66, the previous heat capacity that we found before, times 12.3 degrees Celsius. And when you multiply both of them out, it gives you the answer, which is 229.5 kJ. And remember, one of the most underrated tips for chemistry that it's proven me wrong so many times are the units. You've got to remember the units. So look, when you do this problem, when you like write out your work and then you see that Celsius cancels each other out and it gives you the units that is on course. So far you're trying to find the kJ/mole. You already found the kJ and you're almost sure that you did this problem right if at the end of the problem you do the units right. If you get the right units that you're looking for at the end of the thing, then you know the only error you made might be due to multiplication, which is just you probably put it into the calculator wrong. So when you cancel out the units and it gives you the exact units you're looking for, it instills confidence in your work. So you're like, you're on the right track, which is why I always recommend writing out the units when you solve chem problems. Like for example, if you made a mistake and added mass to this equation at the end, you're going to be left with units that look like this, grams times kJ. And you're going to be like, huh, that makes no sense. And then you look at it, you think about it, and then you realize, oh, I did this problem wrong. And it's not supposed to have mass in it. So that's why I really encourage using units in solving chem. And to finish up the problems, we're looking for the final units to be in kJ/mole. And we don't know the moles. We know the kilojoules, but we don't know the moles yet. And to find the moles, we use this mass that they give us. So we know that ethanol, to save time in the video, I already found the molar mass of ethanol. You know the molecular weight. And you know the molecular weight of ethanol is going to be approximately like 46. This is very approximately 46.1 grams per mole. So now you're trying to find a mole, and the mole of ethanol is equal to the amount of grams you have, which is 10.8 grams times 1 mole of ethanol over the molecular weight, 46.1 grams. The grams cancel out, and then you get 0.234 approximately moles. And now you have the kJ and the moles. What does the unit say to do? Divide both of them. And you don't even have to think about the concept behind it. If you look at the units alone, you know that this is supposed to be beneath this. So to find the kJ/mole, you do 229.5 kJ divided by 0.234 moles. So you can get the energy per mole. And you get the final answer of 980, approximately 0.7 or 0.8 actually, 980.8 kJ/mole, and it's in the right units that they're asking for, and that's your final answer. But also, this is an approximate amount, and throughout this question, when I was doing this question, I rounded up several times. Like here I rounded up, here I rounded up, and also here I rounded up. And advice I'd give you on an actual test, try not to round up the answers to the final one, so you get as accurate as you can, just so you don't miss out on silly points by doing the whole problem wrong, but then rounding incorrectly. Since I already talked about most of the concepts for this chapter, I'll do more practice problems to solidify those concepts. So earlier, I talked about the internal energy, which is equal to the Q plus W. So earlier I touched on this equation and kind of the basic understanding of the concept, but I didn't fully explain it, and I'm going to do so by doing a practice problem based on this concept where you're looking for the internal energy. So the internal energy, like I said earlier, is the heat or the energy of that the system already has plus the work being done on or by the system, which depending on whether it has a negative sign or a positive sign, you're going to add. If it's a negative, you minus because it's a negative, and if it's a positive, you add in the work. But it's just using this formula based off what you get from the problem. So when you read this problem, it's talking about the volume. So you already know there are two different work equations. There's this one, and then there's another one derived from the ideal gas law, which says the change in the moles times the RT. So for this one, you can see that we are given the volume of how much it expanded. So that means we're probably going to be using this equation up here. And then remember, the internal energy, which is what we're looking for, is the heat or the energy the system already has plus the work. And now we know how to solve the work because it's given us the volume and also the pressure right here, the 1 atm. And now we're also given we look for the energy the system already has, which is right here. It says it already has this amount of energy as heat. And so the final answer we're looking for, the internal energy, we know energy, it's an energy, so it's going to have units of an energy. So it's going to have joules at the end. So right here, we know the Q. We don't have to solve anything about that. It's 1.5 times 10 to the 8 joules plus the one we have to find is the work. And to find the work, we plug in the equation, we substitute it in, we have negative, the pressure is 1 atm, so remember the units, they're important, especially in this one. It's 1 atm times the change in volume is the final minus the initial, so 4.1 minus 10 to the 8, times 10 to the 8, not minus. 4.1 times 10 to the 8 minus 3.5 times 10 to the 6, and they're all in liters. And I'm going to plug into a calculator and find out what this gives us. And with the help of a graphing calculator, I was able to get the final answer as approximately 4.07 times 10 to the 8th. And then the 2 units is liters times atm. And now when you try to put this back into the original equation right here, you notice that the Q is written in joules while this unit is written in liters times atm. So you can't just add these two together. So what you have to do is convert, since the final answer has to be in joules anyways, you don't have to convert the energy. You have to convert this work done from this unit to joules. And luckily for you, you don't have to memorize the conversion. That in every exam you take in this class, and included in the syllabus or something like that, there's a unit conversion where it gives you how to convert the units liters times atm to joules. And the conversion for that is, so I'll write it out, 4.07 times 10 to the 8th liters times atmosphere over 1 times 101.325 joules over 1 liters times atmosphere. And then I'll use the calculator again to find the value for this. And the final answer for this is, well, it's about 4.12, I'd say, times 10 to the 10th joule. And then now it's in joules, you can put it back into the final equation, which is change in U. Internal temperature, internal energy is 1.5 times 10 to the 8 joules plus 4.12 times 10 to the 10th joules. And you also use your calculator to get the final answer. The final answer, which would give you 4.13 times 10 to the 10th joules. There's your final answer. For this next problem, we're going to expand a bit more on, once again, the internal energy and the enthalpy. And also, since it's like when you look at the problem, you see moles are given, and we need to solve for the internal energy. Remember, the internal energy is Q plus W, and we have to find work. And then earlier in the other equation, we used volume, the difference, the change in volume to find work. Since there's no volume given here, we're going to use the other formula, which is the change in the number of moles, since we're given the moles to find the work. Okay, so first of all, we write out, you don't necessarily have to do it, but I like to do it, is they say 3 moles of N2 plus 6 moles of H2 give you, and they're both gas, that's another thing to remember, gives you 2 moles of NH3, also a gas. And now, since we're already given a unit of heat here, which is the Q, we know that, remember, when Q is at constant normal conditions, which is normal temperature, which is 25 degrees Celsius, and normal atmosphere, which is always 1 degree atmosphere. When these two, when it's at normal conditions, the Q at normal conditions is the same as the enthalpy. So that's how we already solve for the enthalpy without having to do much work. We just know the enthalpy is equal to the Q at normal conditions. So we already have half the answer. The enthalpy equals to 117 kJ. But another thing that you have to remember when you do problems like this is to make sure you read the question. Right here, it says energy is released. And remember when I told you when a system releases energy, it's a negative, and when it gains energy, it's a positive. Since this energy that is described is being released, it's not staying within the system. So instead of a positive, the actual enthalpy is going to be a negative, whatever the number is, because it's being released, the energy is being released. And that's the enthalpy. And now, to find the internal energy, we know the Q is 117 kJ plus the work. We substitute in the work equation, which is the change in moles times RT. Now we try to solve for the work. And we know the moles, so there are only 2 moles. So it's products minus reactants. Every time in chem, it's always the products minus reactants. And we know there are 2 moles. Like if you look on this side, there are 2 moles over 3.6. There are 2 moles of products minus 3.6 is 9 minus the 9 moles of reactants. So the change in moles is going to be -7. That means that the amount of moles of gas is decreasing times RT. And the R that normally, okay, there are 2 different kind of R's you can use. One in joules and the other, I forgot what the other's in, but it's all in the equation sheet that you're going to get. The R that we're going to use for this one, and the R we're going to use is the R that has units of joules. So since there are 2 different ones, we use the 8.314 joules/mole times K. So the units make sense. And then when we plug this in, it's going to give us -7 moles times 8.314 joules/mole times K. And then the temperature as well, instead of using 25 degrees, when we use T with the units K, we know this K has to cancel out. So the temperature has to be in units of Kelvin, which is going to be 273 plus 25 degrees, which is 298. And then we add that to this equation as well, 298K. And if you notice, the Kelvin cancel out, the moles cancel out, and you're left with just joules. And when you plug this into the calculator, you get -17343 joules, which you can calculate. You can change you should change the units kJ, because the other one's in kJ as well. And when you multiply that, you do that by 1/1000, 1 kJ over 1000 joules. The joules cancel out, and you get 1, 2, 3. The answer should be -17.343 kJ at the end. And the final answer for the internal energy is -117 kJ plus, or what I say, minus -17.343 kJ as well. And when you put that into the calculator, the final answer gives you -134.343 kJ. Among the final topics of the chapter, which is a tricky topic, Hess's law, it basically said that the total enthalpy change for the reaction is the sum of all changes. And enthalpy, remember, is the energy of a reaction. So each reaction, so look here, this is the final reaction you're looking to get, but then there are 2 different reactions that sum up and give you that. And these kind of questions, they're tricky questions. Like, they're not so hard when you finally do it, and they're easy to know when you did it right. But then there can be, like, the really hard ones can be complicated, but this is just the basic idea. And it's a really easy problem to help you understand the concepts of Hess's law. So right here, we're given these 2 equations, and we have to sum them up to get these, like the H2 here, the Cl2 here, and the 2HCl here. And one thing to know is equations on opposite sides of each other cancel out, and how to get. So first of all, the best way to solve questions like this is to look at the different elements and where they are on the table, and then look at these and write them out. Like for this equation, you need a H2 on the left side. Out of all these equations, there's only one H2 and it's already on the left side, so that's a good sign. And then we need a Cl2. Out of all these, there's only one Cl2, but it's on the wrong side over here. And then in the final part, we need a HCl. And right here, when you look at this, there's also locally only one HCl, which makes it an easy problem where it's not overly complicated. And then when you look at it, you see that HCl and Cl2 are swapped. They're in the wrong place. The Cl2 is supposed to be reactant, and the HCl is supposed to be a product. So what you do is, I'll write out the equation again without the grams because that's not important. O2 gives me H2O. And then I'll swap it around and put it in the right place. And when you do that, you multiply this one by -1. And then when it goes to the other side, Cl2 1/2 Cl2 goes on this side plus H2O. And then it gives you, over here, it gives you HCl, which is finally in the right place, plus 1/2 O2. And now when you look at the equation, you see you're still missing something. This chlorine here is a 1/2, and the HCl is missing it's 1 instead of 2. So what you can do is multiply the whole equation by 2. And when you multiply the whole equation by 2, this chlorine goes from being a 1/2 to being a regular 1, which right here. And then the H2O becomes 2, the HCl becomes 2, and the oxygen goes from being a 1/2 to being 2 as well. And also, I noticed this problem does have a mistake in it. The O2 is supposed to have a 2 as well, and the HCl is supposed to have a 2 as well. So then that makes us able to cancel it out here, because the O2's on different sides, so this cancels out, and the H2O's cancel out as well right here, and then you're left with H2 plus Cl2 gives you 2HCl, which is what this equation has to do. And remember, you multiply the second equation by 2 even after flipping it. So then you multiply this by -2, not just 1, since you multiplied it by 2 too. And then to find the total H for the whole reaction, use Hess's law. You add, since this one you didn't do anything to change the equation, it remains -285.8 AJ plus this one 92.3 times -2 right here. And then you add both of them up and you get the final answer for the H's. And this is just a review problem here showing that for combustion reactions, the answer is A, because it's plus O2, and it gives you CO2 and H2O. But then the reason why it's A and not B is because combustion reactions only have 1 mole. This has 1 mole versus 2 moles. And this is multiplied by 2. And that's why it's A. Just something to keep in the back of your mind for multiple choice exams. Something like this could come up on the multiple choice. And finally, this is the enthalpy of a reaction. It's just the sum of the moles times this number, which is going to be provided for you in a table like this. And it's the products minus reactants, just like everything else in chem. It's always products minus reactants. And this is a final easy question for the end of chapter 9, where to do this, it's products minus reactants. And you just do the products, which is 2 times the HF of NH3 is this -45.9. Remember, it's 2 moles times -45.9 kJ / moles, and the moles cancel out. And the final answer is supposed to be left with kg as the final answer. And then minus the reactant side are both 0. So that's 0 plus 0, which is just 0. And then this is the final answer with kJ as your units instead of moles. That's basically the summary of chapter 9 and almost, I think, everything you need to know